part, you know? That's about population dynamic, protein kinetic and genetic.
Yeah.
So for the population dynamic, okay, the simplest deterministic model of population growth is the exponential. The exponential equation. That, you know? Okay, where A is the malnutrition growth coefficient, which is usually a positive constant, but may vary in sign and magnitude with time t to cater for seasonal variation. The
Beginnings of the environment can be modeled by allowing to very randomly add randomly as this.
For a zero mean process, this is a universal at time t. Universal at time t is a Gaussian white noise process. We obtain a linear differential equation either in Ito process. Both the deterministic and stochastic model here admit unbounded exponential growth, which is unavailable in an environment of finite resources. Under such circumstances, a finite supportable carrying capacity K is appropriate, with the population decreasing whenever it exceeds this value. The deterministic model by replacing the growth constant A by the linear factor is. Then we obtain the linear quadratic Verhulst equation, which is often written as with AK replaced by lambda and AX by X. On randomizing the parameter lambda in this equation, we can obtain a stochastic differential equation with this equation. Using the Ito interpretation, which can be solved explicitly by the reduction.
So, let's continue the application to my friend's icon.
Shada and Bila. But from the equation above, some caution needed in randomizing the parameter lambda, or more precisely, the original parameter A and K. Since positive and negative make sense in the growth rate, there are no conceptual difficulties in randomizing the parameter A above. In contrast, by its very definition, the carrying capacity K needs to be positive. So, randomizing it as this equation, the white noise here will lead to unrealistic stochastic model. One way around this is to begin with Schonier deterministic equation, which is this equation. Instead of simpler looking Verhulst equation, to which it reduces with parameters A and K, defined by this equation. We shall not elaborate more on the parameters of the equation, other than to remark that some may take naturally both positive and negative values. Apart from contrived situations, such as laboratory experiments, single species population dynamic models are usually unrealistic in the most nature species coexist with others and are affected by other species one way or another. Such interactions may be benevolent, neutral or malevolent, as in symbiotics, predator-prey or competition, relationships respectively. This can all be incorporated to population dynamics model, with terms coupling together, separating the single species model. A frequently studied deterministic model is the Volterra-Lotka system, which is this system. For I is equal to 1 until D, in the case of D different species. Randomizing the growth parameters A to the power of I as A to the power of I plus sigma I white noise leads to a system of stochastic differential equation. which we shall interpret as Ito equation with independent Wiener process. This process. More generally, we might obtain noise term of the form this. For example, the coupling parameters are also randomized. But for this equation, explicit solutions are not known, so they must be solved numerically, or a qualitative investigation must be made of the boundedness and stability of the solutions.
So that's all for the population dynamics. Get back to the SDE studio. Thank you.
Thank you, Aida, for the information. I will continue with protein kinetic, which stochastic counterpart of many ordinary differential equation modeling coefficients such as Brusselter equation. For example, the kinetic of the proportion x of one of two possible forms of certain protein can be modeled by an ordinary differential equation from this equation, where x is larger than 0 and less than 1, and the other form has proportion y equal to 1 minus x. For random fluctuation of interaction coefficient, lambda of the form can be obtained by this. The appropriate stochastic version is given by Stratonovich's stochastic differential equation with this equation. And the solution of this equation are not known explicitly but remain in interval 0 and 0, 1. Since at both endpoints, the diffusion coefficient vanishes and drift is directed into the interval for positive values of alpha, which necessary for this equation to be meaningful.
Now I will pass the next section, which for Ashraf Mohammed, which he will explain about genetic
application in SDE. We have genetics. The Ito equation equivalent to dxt equals to ast dt plus sigma xt bracket 1 minus xt dwt, where ax equals to a minus x plus lambda x 1 minus x plus 1 over 2 sigma square x 1 minus x 1 minus 2x also has genetical equations. Xt is a proportion at time t of 1 or 2 possible alleles of a certain gene. A discrete time Markov process can be constructed to model the changes from generation to in the allele proportion due to natural selection, which favors the allele most suited to the current state of a randomly fluctuating environment, and to mutation, which in this case transform one allele into the another. Essentially, this discrete time Markov process converges to a different function process xt, satisfying the equation as the total number of alleles become arbitrarily large. Similar arguments have been used to derive a system of Ito equations from Kimura's discrete time Markov model of the distributional dynamics of such an allele amongst differential geographical sites. For example, Shiga obtained the system of equations dxti equals to ar bracket xt to xtd dt plus square root 1 over 2 xit 1 minus xit dwt, where a xt1 to xtd is vi minus ui plus vi xi plus delta I xi 1 minus xi plus sigma mji xj minus xi, where for j1 to tilde, wt1 wt2 to wtd is a Wiener process, and si is a relative fitness of the specific gene in the jth region, and ui and vi is mutation rates between the two alleles in the j region, mij is a relative migration rates from j to I region. So that's all from application in STE for genetics. Thank you.
Thank you, Ashraf Mohammed, for the explain about genetic application. Okay, we hope SDE will apply in many more field in real world application.
So that's the end from the SDE studio.